Welcome to today's lecture. Myself Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The subject that I am covering in my lecture series is Embedded System. Subject code is KOE 062. The topic that I am going to cover in today's lecture is DMA and memory management methods. What is memory? As we all know that memory is very important as a part of any embedded application. It is the physical storage element or the device used for storing two kinds of information. What are those two kinds of information? First is the data or the information, and next is the program instructions, or we can say opcodes, that is the operational codes. The embedded system fetches the data from the memory, we know that. Data is always stored in the memory, processes and produces output data, which is again stored in the memory. So, whether it is the raw data, whether it is the semi furnished data or the intermediate data or the final results, all these things are to be stored in the memory. So, we can understand that how much important is the memory for any embedded system application. The stored data can be intermediate data that is produced during the execution, that is also true. The program information is, what is program information? So, what we were discussing just now was the data, yes, whether it can be raw data or the finished data or the intermediate data. Now, we come to the program information. What is this? It is a set of instructions, or we can say operational codes that executes the function performed by the processor. When the program is executed, the CPU fetches the instructions from the memory and executes it. Again, the processor fetches the code, operational codes, or we can say the instructions from the memory itself. So, data is also fetched from the memory and the operational codes are also fetched from the memory. So, ultimately the memory is the storage device for any system. So, what are the types of memories? Having a brief overview of these types of memories, they can be classified into two types, volatile memory and non-volatile memory. What we understand by the term volatile, that can be vanished. So, when the power is off, then the data is also gone. So, that is known as a volatile. And the non-volatile, when the power is off, the data is retained in the system, it is not gone. That type of memory is the non-volatile memory. So, broadly classified, there are two types, volatile memory. By default, volatile is always random access memory. Non-volatile memory is ROM, that is the read only memory. So, under this, under the category of volatile memory, SRAM, DRAM and DDR-RAM, these three types of memory are included. Under the category of non-volatile memory, electrically erasable PROM, flash memory and SD cards, these are included. So, these are the two types of memories if we broadly classify these. As I have already discussed, that volatile memories will retain the data as long as the power is applied to the memory devices. When the power is turned off, the contents will be erased from the memory. It is used to store the data as well as the program instructions. So, it is not always necessary that the random access memory is used to store the data only, it can be stored used to store the programs as well. It is a type of volatile memory which is divided into two types, SRAM and DRAM, static RAM and dynamic RAM. Non-volatile memory, it will retain the contents when the power applied to the memory device is turned off. Using this memory, the stored data can be retrieved after restarting the system. Boot up configurations are typically stored. So, this type of memory is used to store the boot up configurations, because they are always needed whenever the system is powered up. They are slower than the volatile memory, but more information can be stored for a longer time. So, different types of non-volatile memories are available in the market, different types of non-volatile memory chips are available, and we can make selection from those. They are classified into categories, that is electrically erasable and mechanically erasable. Yes. So, when we manually erase the data through the connections, physical connections, then it is the manual that is mechanical erasable. But when we do it by using the ultraviolet radiations, then it is electrically erasable. So, the various examples are the EEPROM flash memory, these belongs to the electrically erasable category, and the disk drives magnetic tape, these comes under the category of mechanically addressable mechanically erasable categories. Another important topic as a part of memory units is the direct memory access. What is this? It is a method that allows an input or output device to send or receive the data directly to or from the main memory without the intervention of CPU. So, it bypasses the CPU to speed up the memory operations, because suppose the CPU is busy in some other job. So, the system has to wait for the buses to get released, for the CPU to get free. So, it increases the processing time, but when the system bypasses the CPU and the input output device send or receive the data directly to the memory without using the CPU, then the system speed gets increased. This is what is happening in this DMA operation, and this process is managed by a chip known as the DMA controller, that is DMAC. Data transfer occurs efficiently between the input output devices and system main memory with the least intervention of processor using DMAC. So, this is how this operation is done. Let us see the details. What is the process behind this? This is the whole diagram which is presenting the DMA operation. Whenever an input device wants to transfer the data to or from the memory, okay. So, we are dealing with the memory only. It sends the DMA request DRQ to the DMA controller. So, this is the input output device and it wants to communicate with the memory, yes, directly without using the processor. So, what will happen? It will send the request to the DMA controller, this is the DMAC, through DRQ. So, DRQ is the signal line through which the request is sent from the input output device to the DMAC, that is the direct memory access controller. DMA controller accepts this DRQ and asks the CPU to hold. This is a CPU. So, now the DMAC has received the request from input output device. Now, it will ask the processor to hold for a few clock cycles by sending the request through the hold signal, HLD signal. Now, what will happen in the third step? The CPU receives the hold request. Now, CPU has received the request through the hold line from the DMA controller and relinquishes the bus and sends the hold acknowledgement signal. What is this? What is happening here? That is now input output device has sent the request to DMAC. DMAC has sent the request to processor to hold on the job being done by this processor for few clock cycles. So, now this request is received by the processor. Now, the CPU will relinquish all the buses, that is intentionally, that is by desire, it will leave all the buses, it will free up all the buses and then sends the acknowledgement signal to the DMAC. What is this acknowledgement? That yes, I have received the request and I am making all the buses free for the processing of DMAC. Now, what will happen? After receiving the hold acknowledgement, now the hold acknowledgement has been received, DMAC acknowledges input output device, that is that the data transfer can be performed and DMA controller takes the charge of the system bus and transfers the data to or from the memory. So, next what is happening? So, that ultimately who was making request? Input output device through the DRQ. Now, after getting the acknowledgement signal from the CPU, DMAC will send the acknowledgement signal to the input output device also. What is this signal doing? This signal is telling the input output device ki yes, that the buses have been freed up by the processor and now the DMAC is having the control of the buses and the direct memory access request has been acknowledged and the direct memory access can be done. When the data transfer is accomplished, the DMA raise an interrupt. Suppose now the whatever the memory operation was to be performed, whether it was reading or writing, it has been performed. Now, what will happen? That DMA will raise an interrupt to let know the processor that the task of the data transfer is finished now and the processor can take the control back. Which control? The control of buses. So, now ultimately what is happening? That first of all the request was sent from an input output device to the DMAC. DMAC was sending the request to the CPU. CPU was acknowledging that request and sending the acknowledgement signal to the DMAC and then after that DMAC will send the acknowledgement signal to the input output device, because input output device was the one which was making the request. So, after receiving the acknowledgement signal, then the memory access operation is performed and finally that DMA will raise an interrupt to let know the processor that yes, we have done our job and now you can take the control of the buses back. So, this whole operation is being done in the DMA process. This is what is happening in DMA. So, what are the different modes of data transfer in the DMA? That first is the single transfer at a time, that is the byte by byte the data transfer is taking place. Next is the burst at a time and the third is the bulk transfer. So, the burst mode is temporarily high speed data transmission mode to facilitate the sequential data transfer maximum throughput. So, the burst mode data transfer rate speeds can be approximately 2 to 5 times faster than the normal operation. So, in the high processing speed applications, the burst mode should be used. What are the different advantages? That it will speed up the read write task, because the wait time for the CPU is not there in the system. So, the system becomes fast. DMA reduces the clock cycle required to read or write a block of data. So, implementing DMA also reduces the overhead of the processor. So, all these are the advantages. Disadvantages: since it is extra hardware unit, it will obviously increase some load. The cost to implement the DMA controller in the system is increased. The cache coherence problem can occur while using the DMA controller. Yes, so these are certain disadvantages of the system. Now, when we are talking about the memory, so memory management is a very important. So, what all features come under the memory management unit? That the runtime mapping from the virtual to physical addresses, managing the mapping between the logical logical memory and the task memory in references, determining which processes to load into the available memory space. There are few more responsibilities like allocating and deallocating of memory for processes that makes up the system. So, this is very important that at what time the memory is to be allocated or deallocated from a certain process taking place. Supporting the memory allocation and deallocation of the code requests within the process such as the C language alloc and dealloc functions. So, we must be remembering that when we studied the C language, there were certain functions like alloc and dealloc which were used to allocate or deallocate the memory, or specific buffer allocation and deallocation routines tracking the memory usage of system components, ensuring that the cache coherency for systems with the cache. So, this is very important when we are using the cache memory in our systems to speed up the processing, then we should take care that cache coherence should be avoided. Ensuring the process memory protection. Now, so there are certain schemes to handle this memory management part. So, there is the swapping, next one is the paging, and the last one is the segmentation. So, what is happening in the swapping is that our logical memory is allocated to various processes, right. So, when we are handling them, when the processor is handling the multiple processes at a time, what is happening, the memory is divided into different processes, it is being allocated to different processes. So, this is a main memory, and if we want to speed up our system, what we should do, that we should keep those processes one by one aside, so that the main memory can be used for other processes. So, how can this can be implemented by using the secondary memory. So, what is happening in this swapping scheme is that after the certain process has been done, then it is being swapped to the secondary memory, and meanwhile the primary memory is used by other processes. This is happening in this scheme. So, let us have a look at this diagram, that this is the main memory and it has been allocated to different processes like process 1, process 2, process 3, and now what is happening, P1 goes from input output wait, P1 goes for input output wait, that is that it has been swapped out to secondary. This is the secondary memory. Now, again after the other processes has been executed here, the process 3 will swap in again. This was the swap, P1 comes back after input output and the process 3 swaps out here, and then again process 3 swaps in again, and finally the process 1 swaps in again. So, this is the mechanism in which a process can be swapped temporarily out of the main memory, or we can say it can be moved out to secondary memory, that is that can be at the disk and make that memory. So, during this what will happen, it will make the memory available to other processes. At some later time, the system swaps back the process from the secondary storage to the main memory. This is happening in this diagram, that one by one these processes are being swapped to the secondary memory, and after certain time when the other processes have been done, then the process that was swapped out to the secondary memory goes back to the main memory. This is happening. So, it helps in running multiple and big processes in parallel. So, in this way the multiple and the big processes can be executed simultaneously. Therefore, swapping is also known as the technique for memory compaction. In this way, the same work can be done in compact memory, not a large memory is needed for these purposes, because we are using the secondary memory along with the primary memory, and in this way the swapping can be done and the two memories goes hand in hand to make the things happen. So, in this way swapping is very good option for memory management. Another option is the paging. What is happening in this paging scheme, that a computer can address more memory than the amount of physically installed in the system, and how this is done, that the paging plays an important role in implementing virtual memory. So, this is happening is that in the paging is the memory management technique in which the process address space is broken into blocks of the same size called pages. So, the memory that has been allocated to the processes, that memory is broken into different size in the same size pages, and that size is in the power of 2, that is between 512 bytes and 8192 bytes. The size of the process is measured in form of the number of pages, in the terms of number of pages, that is the page number, which is equivalent to logical address, that is given by the page number plus the page offset. Similarly, the main memory is divided into small fixed size blocks of memory called the frames, and the size of the frame is kept the same as that of the page to have the optimum utilization of the main memory. The frame address, that is a physical address. So, here the page address was the logical address and the frame address is the physical address. This is equal to the frame number plus page offset. So, in this way the paging scheme is implemented to make the memory more efficient by dividing the logical memory space into number of pages and also dividing the main memory into number of frames and mapping these pages and frames together. So, this is what is happening in the paging, that this is the logical address space and it has been divided into page number 0, 1, 2 and so on up to page n, and this is the main memory. This is being divided into number of frames f 0, f 1 and so on up to f n. And this, what is this happening, that each page is mapped to certain frame. So, in this way the whole of the physical memory can be used, it can be efficiently used to map the various processes which are being done, which are being handled in the application. The data structure called the page map table is used to keep the track of the relation between the page of a process to the frame in the physical memory. What is happening in this page map table? There is the page number and there is another frame number, and in this way both these are mapped together, and whenever the processor has to address any process, then what will happen, that it will map to the particular frame present in the main memory, and in this way that the page those pages can be mapped to the main memory and the main memory can be efficiently utilized. Last scheme in this section is the segmentation. In this, this is very much similar to the paging, except for the fact that in the pages were of defined size, of the same size, but the segments are of different sizes according to the requirement, according to the load. So, what is happening is in this is the main memory is divided into the chunks of memory, that those are known as the segments, and the segments are used to store the different sections of the process. We know that within a process there are the stack operations taking place, there is the data, there are the programs, the code. So, the different segments are used to store the different types of data, that is one segment must be storing some data, another segment must be storing some stack operations, another one will be storing some program codes. So, these are known as the segments. The segment is a set of logical addresses containing the same type of information. So, again the segment physical memory address is the segment number, that is a base address plus the segment offset. In this the whole memory is designed. So, this is how the mapping is done. These are the different processes which has been divided into segments, and this is the segment map table. This is the main memory. Here the segment has been mapped to different locations, like this is segment 1 mapped to this location, again the size is 400 here. Segment 2 the size is 200, it will take 2 slots. Now, again the size is 100, it will simply take 1 slot. Here the size was 400, so it was taking 4 slots. So, in this way this segmentation is being done. So, that is it, that is for this lecture. In subsequent lecture we will talk about further sections related to the embedded system application. Thank you.